Ajit? Is that did I say that right?
Ajit.
Ajit. Hi, I'm Doug. I'm one of the organizers. What are you going to talk about?
Right there.
Polymorphic malware.
Yes, polymorphic malware. That's pretty cool.
That's easy for you to say.
I'm trying to think of something. Anyway, are we starting?
Yeah, I dare you to be folksy about polymorphic malware.
That's just reading his crib sheet.
So we're ready to start? Sorry about this. Am I going over? Uh-oh, it sounds like we need to start. Okay, Ajit, right?
Yeah, Ajit.
Ajit.
Yes.
Okay, so once again, my name is Doug Spinner. I'm one of the organizers for BSides this year. And I want to thank everybody for attending. If you got a problem, talk to the other people. If you like it, talk to me. That's the way we run things here. So Ajit, right? Ajit.
Ajit, yes.
Ajit.
Yes.
I'll get it right by the answer. I'm not going to try your last name. Advanced techniques for real-time detection of polymorphic malware. And I got to tell you, I got some in my pants right now that I'd like for you to analyze.
Okay.
Take it away. I'll let you go for it.
All right. Well, first of all, I really want to apologize, for this talk. It's kind of technical. I didn't realize that I needed to add a lot of cats pictures and dog pictures and make it really, really funny. I will do that the next time. Okay, I promise. And this is a little bit as I said, on the technical side. I will try to make it as humorous as possible. And feel free to stop me at any time if you have any questions. I know that you guys want to head out somewhere probably really soon, and I'll try to do my best. Okay. All right, there we go. Cool.
Friends at home want to hear you.
Totally.
Yeah.
Thank you. All right. So my name is Ajit Thyagarajan. I am currently an independent security researcher. I used to be at Fidelis before this. Actually, if there are any Fidelis people over here, for the rest of you guys, I'm actually in stealth mode right now. So it's just me. Oh, sorry. Okay. Don't move. Okay. All right. And prior to this, until about 2 months ago, I was at Fidelis, in various director roles over there. A shout out. A lot of this research was done while I was at Fidelis. This was in the summer of last year. I had an intern from University of New Haven. His name is Vic. And he helped me on a lot of these projects and trying to run in terms of running the experiments and so on. So a big shout out to him for actually getting a lot of this work done, and of course for Fidelis for providing a lot of the data. So what exactly am I trying to do over here? This talk is actually a little bit about just looking at malware, which is something that we did a lot of, trying to make some sense of what are some of these patterns that we're seeing, and try and improve detection. So the Fidelis box, for example, is a network security device. We scan malware as it goes by in and out of an organization, and then we try to do it really, really fast. So one of the requirements was that how can we improve our fast detection techniques for malware, and that's what this sort of research was focused on. So malware generally is distributed through multiple ways. Just a couple of them listed over here. You got malicious websites, email, you get malware in email, phishing, spam, and then if you happen to be infected by some kind of a bot or something like that, then there's malware that can come in over command and control channels as well. So those are just the various mechanisms for distributing malware. Now on to detection techniques. So there are various types of detection techniques, and usually you try each one. So if, for example, you get a file and you see that it matches a list of matches one amongst a list of signatures that you potentially have, then you can say, okay, you know what, it's an exact match. It's probably this malware. You probably have some attributes that go along with that signature, and you can say that, okay, I'm done. it's malware, I can rest. If not, then you move on to some kind of static analysis, and then heuristics, and then ultimately to emulation where you have like a sandbox type environment and so on. And the key here is that you can see how the time scale sort of progresses. So signature-based detection literally is in the microsecond, range, all the way up to, several minutes for doing emulation. So if you can somehow get your detection as close to, microsecond, millisecond as possible, then your speed of detecting malware obviously is significantly higher. So, so you want to sort of focus on those techniques that you can do really fast detection with, rather than the heuristics and emulation techniques, because obviously you can't send every single file for emulation analysis. It's just not going to work. So what we were trying to do was we get this report every day of malware that our various sensors have seen in the field. And what we were noticing is that we saw a particular file, that was determined to be malware. And we would see like a boatload of MD5s associated with that one particular file. So obviously signature matching was not working for that particular file. And also, why were we seeing so many different MD5s for the same file? So we analyzed that a little bit more and found that these were malicious websites that were continuously modifying the files on the web server itself. Okay, so and this type of modification is called polymorphism, in case you're not familiar with that term. And what they do is the code or the file is altered by changing a few bits, or you can do encryption, or you can obfuscate, but ultimately the characteristics of what the file does is exactly the same. Okay, and as far as polymorphism itself is concerned, the server-side polymorphism is what we were observing with these multiple MD5 files that we were observing. And there are two different techniques that we saw. We saw sites that did volume malware. So, for example, they would send out a mass email to millions of people with like some URL in there so that the file name stayed the same for everyone. And then as people clicked on those links and went to that website, it would then serve out new variations of that file by just altering the file just slightly. Compare that with on-demand malware, where it's a much more targeted attack, where they can encrypt it and obfuscate it and so on. But then it obviously takes a lot more time to do these things, and therefore volume malware, just has a few bits that are modified. And so what our goal was to try and see if we could figure out or detect this volume malware, which was escaping our signature-based detection, using some other technique that was really fast, rather than doing the static, heuristic, or emulation-based analysis. And again, we couldn't tell at that point which one of those were actually being hit. We definitely knew it was not signature-based. And what our goal was to try and see if we can detect that using something close to signature-based analysis. Okay? Is everybody with me so far? Okay, cool, awesome. So, enter SSDeep. So, how many of you guys know SSDeep? Okay, I see a couple of hands over here. Okay, so SSDeep is essentially an algorithm for figuring out what is called a fuzzy hash of a file, as compared to like the MD5 or the SHA-1, SHA-256, and so on. So the way it works is that the algorithm sort of cycles through the file, and then it breaks it up into chunks, and then hashes each one of those chunks into a single byte, and then concatenates all of that. So it's sort of like a compressed representation of that entire file. I mean, I don't want to go into the details of how SSDeep works. You can just Google SSDeep and you'll find a whole bunch of hits on that. And essentially you get a what is called an SSDeep hash or a fuzzy hash. Okay, and this diagram sort of gives you an approximate idea of how that works. And a lot of malware sites today compute this SSDeep hash. So, for example, this little snippet here is from VirusTotal. You can see that amongst the malware properties, which include, MD5s and SHA-1s and all that, the SSDeep hash is also provided, and pretty much all of the popular malware analysis sites provide that as an attribute for the malware file. Okay, and so how do you use this? So primarily for comparison. Okay, so the SSDeep algorithm that you can download from from SourceForge, I think it's SourceForge or wherever it's hosted right now, has a mechanism to compare two files. So what it will tell you is that if you give it two files and run SSDeep on that, it will tell you that, hey, you know what, file 1 matches file 2, and then it gives you a little score at the very end. And that score will tell you how close those two files are together. Okay, so in this case over here, file 1 matches file 2, 99% of, they're identical. Of course, they're completely identical, it'll give you 100. But in this case, maybe there was a very small difference between the two files. And then again, if you do file 3 matches file 4 with 44, that means that there's a significant difference between that. But there is some commonality elements in between the two files. And another use case for something like SSDeep is in grading exam papers or reports. So what they do is they look at two answers and see if there's like a similarity between these two in terms of the words that they use and so on. And just a side note. Anyway, so back to what we were trying to do. I showed you this report that we were analyzing, and we saw all these files that had different MD5s and but the same file name. So what we did was we started looking more closely into those files. So in this case, we looked at this thing called da-ticket.exe. This was a campaign run by some malware author out there. And if you just went to VirusTotal, typed in da-ticket.exe, it gave us literally thousands of entries. So obviously, a lot of the malware vendors had submitted these files for analysis to VirusTotal, and they had copies of all of those files. So in addition to what we had, I also downloaded a whole bunch of samples from VirusTotal. And in here, you can see that the last field, like in this first line over here that says 0074, that's actually the MD5 of the file. And every one of these has a different MD5. And the very first, the first field, which has a bunch of numbers in there, is the beginning of the SSDeep hash. Okay, so all of these are the SSDeep hashes. What it shows is the block size. There are 2 hashes, and then the file name. And if you start looking at the way these hashes are constructed, like if you look at the second and third entries, you'll start seeing that there is the same characters that start occurring until probably like somewhere close to the very end. So that just sort of shows you how similar they potentially are. So then we started digging in further into these files. So just did a quick hex dump of the file itself, and notice that there's just one line that is being continuously modified between a lot of these files. And on the right over here, we did the results and found that over 1,000 files had a 99% difference, a 99% similarity between each other. Okay, so clearly there's polymorphism out there, very, very rampant. Now the question was, so how can we use SSD potentially to improve our lookup? Because that's that was the key goal of trying to use something like SSD to do lookups. I mean, you can do comparisons between 2 files. If you've got a malware file or 2 malware files and you compare them, sure, you can find out whether they're similar or not. But then now I receive a malware file for analysis. I have a whole bunch of SSD hashes. Am I going to sit and compare every single one of them? So that's an order n problem in some sense. It's just going to take way too long. So that's the SSD lookup problem in some sense. So you got an input file coming in. We have a huge list of a huge database of hashes, and then we literally have to compare every one of these hashes to figure out which one is the closest and if there's a close match in there at all. So SSDeep didn't look so good there in its base form in the way they had structured the code, and so obviously we needed to make some changes, and we thought long and hard about this particular problem. So what we did was we decided that, okay, we would take that hash and then we would break it up into chunks and then create an index of each one of those chunks and then try and look up each one of those chunks individually and make a little linked list if there were additional entries in there, and then link it back into the main hash database. And that immediately gave us a significantly high rate of lookup, almost like order 1 in all of our lookups. So that was a huge win for us in terms of how we can do lookups using SSDeep and not having to do a file comparison with every single hash. So the next question was then, okay, so we've got the SSDeep lookup now working pretty well, but how do we create this hash database? Do we take all our malware samples, and if we just stick them all into the hash database, then we're going to have a very, very large database, and there's going to be a lot of similarities in that database itself. So our next problem was to sort of figure out, okay, how can we optimize the database itself? So in this case, the problem became, okay, I've got a input file. I'm going to stick that into the database. And the question is whether I need to or not, or if there's something else that's already similar to that particular file. And we played around with a couple of algorithms. What we did was, while we were inserting the file into the database, we found that there was almost always a natural hit if there was one already in there. We can set various thresholds in there. And if there was, then we could apply one of many algorithms in terms of either replacing the new one with the old one, keeping the old one, or if the threshold was low enough, just add it in there as well. So those are some of the database optimizations that we had made. So, any questions so far? Okay, cool. Good here. Okay, so that's essentially the main techniques that we developed for using SSDeep from a lookup perspective rather than just a comparison of two files. Now the question was, is SSDeep really the gold standard for doing fuzzy hashing? And the answer is probably not. And I'm really surprised that it hasn't been replaced by all these malware vendors by something that's a little more powerful, a little more current. So first of all, this technology is circa 2006. That's when it was first developed. And since then, there have been multiple algorithms, such as MV hash, SD hash, SIM hash, some by Google. And then there's this whole area of approximation matching that some researchers have been working on. And there are some experiments being done right now in comparing the effectiveness of these algorithms with SSDeep. And in almost all cases, they find that these newer algorithms way, way outperform what SSDeep does. One more thing is that SSDeep actually has a limitation in that you can't compare two files that are very different in terms of their size. So the initial block size does matter a lot. So if you create another file that is actually identical in terms of its content, but then you just pad it with a lot of zeros or no ops, then the SSDeep algorithm sort of doesn't work so well. So it does have those limitations. And the next thing is that as we started looking into more of these files, malware files that we were detecting in the field, we began to see a small trend in malware authors going from polymorphic malware to like metamorphic malware. And what this means is that polymorphism is just simple changes in the files. Like, as I said, a few bits change, encoding, encryption. Whereas metamorphism is more about just changing the overall structure itself, but the behavior tends to be the same. So we're seeing that happening as well. So we're getting less and less hits now in terms of the different MD5s and the same file. So the thing is, I think now what we are thinking is maybe there's something like machine learning that might be a better fit for detecting these sort of approximations and so on. And that's something that we're exploring right now. Okay? I think I did it pretty well here. So,
You did great.
awesome. Thank you. Any questions? Yeah, go ahead.
So I'm assuming you trained this on a Windows corpus, is that correct?
On a what?
I'm assuming you trained this on a corpus of Windows malware, is that correct?
That is correct. We only use exe files currently, yes. We have not done it, but the same concept can be applied to any of those as well. Sure. Yep.
If it's encryption that's changing, isn't the entire SSD going to basically change?
That is correct. So encryption wouldn't work over here. What you have to do is you have to unencrypt it and then work on the unencrypted file. So with encryption, that's the issue. And again, you can also do things like you can take a memory dump off every single file and then analyze that, compute an SSD hash of that, and then go there. So you can actually do it at multiple stages depending upon where your comfort level of operation is. Yep.
So I think traditionally with the polymorphic malware, the malware developers would use like cryptors to use kind of standard encryption formulas to make unique samples. But usually like the stub is exceptional. But now I've been noticing that you can use something like opaque predicates that succeed like dead code. So normally when malware developers insert dead code, it's specific to one function. But if you can insert opaque predicates that are like a few functions deep, it might like completely remove the ability of like standard AV detection. Have you seen anything with SSD being able to detect that?
Oh, absolutely. So the thing is, SSD in its raw with its raw binary format analysis will completely fail in those cases. So what you have to do is you have to take every one of these files and sort of normalize it, which is you have to, as I said, go the ultimate mechanism for using SSD is to get a memory dump so that you eliminate all those, no ops and all that kind of stuff, and then see if you can apply it on that. So that's sort of the only way right now, and as I alluded in my last few slides, even that can potentially be subverted by malware authors today. There's a huge trend towards towards metamorphic malware where they change the entire set of instructions. Like, for example, instead of register A in the memory, they will start using register B. And then, change an order of instructions such that it does the same thing, but then in different sequences. Ultimate behavior is the same, but, you have different ways of sequencing things. And all of those things will completely defeat something like SSD.
I've been thinking about stuff like if you use assembly language, like just like the normal assembler, or even something like Java bytecode or like CLR, where you can kind of control the structure more so than you would if you just use like GCC, then you would be able to evade most of these kind of detection mechanisms because you're able to decide like what register you're going to use, and then you can just kind of have another pass over the compiler. Say like, I'm going to change. You kind of have like semantically equivalent code generation. So it's not necessarily metamorphic like what you had in the 90s. You kind of make it.
It's somewhere in between, basically.
Yeah.
Yeah. I'll give you my business card. Please get in touch with me. I'd love to hire you.
So, just because I'm tired, I'm going to check this.
Any other questions?
Here,
Yeah, one more.
question.
Two related questions.
Okay, sure.
BSides